October 15th, 1991. Utah desert. Middle of the night. A detector picks up something impossible. A single subatomic particle. Smaller than an atom. Invisible to the naked eye, moving at the speed of light. That's not a typo. 23 nines. If this particle raced against light for an entire year, it would lose by less than the width of a human hair. But here's the crazy part. This single particle carried the same energy as a baseball thrown at 60 miles per hour. Except it wasn't a baseball. It was a proton, one tiny proton with the kinetic energy of a fastball. Scientists called it the "oh my God" particle. And to this day, nobody knows where it came from. What are cosmic rays? Right now, as you're watching this, invisible bullets are tearing through your body, thousands of them every second. They're called cosmic rays, not actually rays, particles, mostly protons, sometimes helium nuclei or heavier atoms, all stripped of their electrons, racing through space at incredible speeds. Most cosmic rays are harmless, low energy. They hit Earth's atmosphere and fizzle out. We barely notice them. Some come from our sun's solar flares, shoot them out constantly. Others come from supernova explosions across the galaxy. Dead stars are going out spectacularly. The typical cosmic ray carries about 10 billion electron volts of energy. It sounds like a lot. It's not. The Large Hadron Collider routinely accelerates particles to 14 trillion electron volts. The "oh my God" particle? 320 exa-electron volts. That's 320 billion electron volts. 50 joules of energy. Enough to power a 40-watt light bulb for over a second. All packed into something a trillion times smaller than a grain of sand. Nothing humans have ever built comes close. The night it hit, the University of Utah runs a detector called Fly's Eye. Arrays of telescopes stare at the night sky, waiting for cosmic rays to slam into the atmosphere. When a high-energy particle hits air molecules, it triggers a cascade, a shower of secondary particles. The air glows faintly blue. For just a fraction of a second. Fly's Eye captures that flash, measures its height and intensity, calculates the original particle's energy. On that October night in 1991, a researcher was working a shift in an old trailer on a desert mountain. The detector picked up a flash. He ran the calculations. Error. Must be a mistake. He ran them again. Same result. 320 exa-electron volts. He triple-checked the instruments, looked for glitches, equipment malfunction, anything that could explain it. Everything checked out. The particle was real. Word spread through the physics community. Initial reaction? Disbelief. Maybe the detector was wrong. Maybe the energy calculation was off. Follow-up observations over the next few years detected more ultra-high energy cosmic rays. Not as powerful as the "oh my God" particle, close enough to confirm the phenomenon was real. Physicists had to accept it. Particles this energetic actually exist. The question became, how? The speed problem. Let's talk about how fast this thing was moving. At 99.999 seconds, 51%, the speed of light, relativistic effects kick in hard. Time dilation goes crazy. From the particle's perspective, time almost stops. If it could somehow maintain that speed, it could cross the entire observable universe in a couple of weeks of its own time. Proxima Centauri is 4.2 light-years away. For us, that's over 4 years at light speed. For the "oh my God" particle, 0.43 milliseconds of its own time. Light still wins the race. Nothing with mass can reach light speed. Einstein's laws are absolute. The closer you get, the more energy it takes to go faster. Accelerating the "oh my God" particle to that speed required an unimaginable amount of energy. Whatever created it must be one of the most violent, powerful objects in the universe. Supernovae? Not even close. A supernova explosion releases enormous energy, enough to outshine an entire galaxy for weeks. Still not enough to create a particle like this. You need something more extreme. Active galactic nuclei. Supermassive black holes consume matter. Magnetic fields are millions of times stronger than anything we can create on Earth. Even then, the physics is barely understood. The GZK limit. Here's where it gets weirder. According to physics, the oh my god particle shouldn't exist. In 1966, 3 physicists independently calculated a limit. Kenneth Greisen, Vadim Kuzmin, and Georgy Zatsepin. They figured out the maximum energy a cosmic ray can have if it travels long distances through space. The limit? About 50 exa-electron volts. Why? The cosmic microwave background radiation left over from the Big Bang. It fills all of the space. Faint glow of microwave photons. When an ultra-high energy proton slams through space, it collides with these photons. At high enough energies, those collisions create new particles, pions. Each collision drains about 20% of the proton's energy. After traveling 160 million light-years, a proton above 50 exa-electron volts will lose so much energy that it falls below the limit. The universe itself acts as a speed trap. This is the GZK cutoff, a cosmic energy ceiling. The oh my god particle clocked in at 320 exa-electron volts, 6 times higher than it should be. Either the particle came from somewhere nearby, within the GZK horizon, or our understanding of physics is wrong. Scientists traced its trajectory backward, pointed telescopes at where it came from nothing. No active galaxy, no supermassive black hole, no obvious source. It came from an empty region of space. Amaterasu, history repeats, May 27, 2021. 30 years after the oh my god particle, the telescope array in Utah detects another monster. Energy, 244 exa-electron volts, the second highest energy cosmic ray ever recorded. Scientists name it Amaterasu after the Japanese sun goddess. Same problem. They trace it back to its source. Find nothing. Amaterasu appears to come from the local void, an empty region of space bordering the Milky Way. No galaxies, no stars, nothing powerful enough to create it. You trace its trajectory to its source, and there's nothing high energy enough to have produced it, said John Matthews, one of the researchers. It's like you've got a gorilla in your backyard, throwing bowling balls at you, but he's invisible. 2 of the most powerful particles ever detected. Both are pointing to empty space. Both defy explanation. Several possibilities exist. Maybe magnetic fields in space are stronger than we think. Strong enough to bend even these ultra-high energy particles, deflecting them from their true source. Maybe there's new physics we don't understand. Exotic particles, undiscovered interactions, something operating beyond the standard model. Or maybe these particles come from cosmic defects, colliding cosmic strings, tears in space-time itself. Nobody knows why it matters. Since the oh my god particle, scientists have detected hundreds of cosmic rays above the GZK limit, not as energetic, still way above where they should be. The Pierre Auger Observatory in Argentina, the telescope array in Utah, both facilities cover hundreds of square kilometers. Arrays of detectors are waiting for these rare events. Ultra-high energy cosmic rays are incredibly rare, about 1 particle per century per square kilometer. You need massive detector arrays to catch them. Each detection adds another piece to the puzzle. Where do they come from? How do they form? What accelerates them to such insane energies? The answers could reveal new physics forces we haven't discovered, particles we haven't detected, maybe even clues about the structure of space-time itself. These particles carry energies millions of times higher than anything we can create in particle accelerators. They're natural laboratories for extreme physics, testing theories at energy scales we can't reach any other way. Understanding them could explain the most violent processes in the universe, the formation of supermassive black holes, the behavior of matter at extreme densities, the limits of what's physically possible. Think about that. Right now, somewhere in the universe, something is accelerating particles to speeds we can barely comprehend, packing more energy into a single proton than should be physically possible. And occasionally, one of those particles finds its way to Earth, traveling for millions of years across the void, moving so fast that time nearly stops, carrying energy that breaks our understanding of physics. We caught it, measured it, named it. We still have no idea what created it. The "oh my God" particle proved the universe is stranger than we imagined. More violent, more extreme, capable of things we thought impossible. Every time we look deeper into space, we find something that challenges everything we know. Ultra-high-energy cosmic rays are just one example. A reminder that we're still beginners, still learning the rules. The fastest thing in the universe isn't light. It's a particle we can't see from a source we can't find, breaking laws we thought were absolute. And it's heading toward us right now. Want to explore more cosmic mysteries? Hit subscribe. We're diving into rogue black holes, dark matter candidates, and the fate of the universe next. Drop a comment on what we should tackle next. The universe is full of impossible things. We're just getting started.